Good evening. How's it going? It's day 8. It's Advent of Code. We're still going strong. We've done 14 problems, and welcome back to Advent of Code and Elm, day 8. My name's Ryan. I'm a web developer. We've been doing things in Elm together in Ellie for a few videos now. I've got this little template here, so we can write some code on the left, see the output on the right. For those of you who haven't seen the series, every day Advent of Code is releasing a new problem in December, and there's 2 parts to each problem. Yesterday we did some stuff with like a terminal line. There should be a link to the playlist somewhere near my face. But we solved the problems together, and then I share the links in the video description below. So you can run it on your own computer if you want. You can pause the video, try these out yourself. You can go to adventofcode.com. Click on day 8, and then there's going to be a prompt. I haven't read it yet, so I'm about to click on it, and yeah, let's see how it goes. Let's dive in. Day 8, top tree house. Okay, so our elves they're trying to get stars, going in a jungle. I don't know. Anyway, the expedition comes across a peculiar patch of tall trees, all planted carefully in a grid. The elves explain that a previous expedition planted these trees as a reforestation effort. Now they're curious if this would be a good location for a treehouse. First, determine whether there is enough tree cover here to keep a treehouse hidden. To do this, you need to count the number of trees that are visible from outside the grid when looking directly along the row or column. The elves have already launched a quadcopter to generate a map with the height of each tree. Your puzzle input, for example. 3037. Okay, so this is our little sample input. Each tree is represented as a single digit whose value is its height, where 0 is the shortest and 9 is the tallest. A tree is visible if all the other trees between it and an edge of the grid are shorter than it. Only consider trees in the same row or column. That is, only look up, down, left, or right from any given tree. So like if we were looking at this tree, we would only look at the things above it, the things below it, the things to the right, and the things to the left. All of the trees around the edge of the grid are visible. Since they are already on the edge, there are no trees to block the view. In this example, that only leaves the interior 9 trees to consider. The top left 5 is visible from the top and from the left. It isn't visible from the right of the bottom since trees of height 5 are in the way. So there's a tree of height 5 kind of blocking the view if you were looking at it from that way. Top middle 5 is visible. The top middle 5 is visible from the top and the right, but not the left. Top right 1 is not visible in any direction. For it to be visible, there need to only be trees of height 0 between it and the edge. Left middle 5 is only visible from the right. 3 is not visible from any direction. Right 3 is visible. Okay, so these are all just examples here. In the bottom row, the middle 5 is visible, but the 3 and 4 are not. So, got it. So, cool. With 16 trees visible on the edge and another 5 visible in the interior, a total of 21 trees are visible in this arrangement. Consider your map. How many trees are visible from outside the grid? Okay, cool. So we're going to start this puzzle by just taking in this sample input and trying to turn it into something that we can work with. So all we have so far is just this string trim function to get rid of this like new line from when I pasted. We're turning the string into basically wrapping it in quotes here so that we can print it out with HTML text. And so what we can do is we can start using Elm's pipeline syntax to start calling functions on this puzzle input. So puzzle input's a string. If we call string.lines, it's going to turn it into a list of strings. So now we have 5 items in our list, 1 for each line that we have here. Similarly, I think what we could do is we could probably, for each one of these, I think we can do a string.toList, and that's going to turn each item here. Each basically line is going to become a list of characters. So now we're going to have a list of lists. So you'll see there's this nested list of lists. Great. I want to turn these characters into integers. So what I'm going to do is for each one of these lines, I'm going to loop through each character. And let's see if there's a character to int function in the core library. So I'm going to search for toInt. Looks like there's only one from string to a maybe integer. So I think what I'm going to do is instead of using string to list, I'm going to use string.split here. So what that'll do is on the right, you can see these are single quotes. That's Elm's character type. So if I do a string.split, what's going to happen is it's going to give me a list of strings. So this is an example of splitting on commas. If this is our input string, it would give us cat, dog, and cow. If we do split on empty strings, what it's going to do is it's going to do the exact same thing, except these are all individually going to be wrapped in double quotes. So what I'm going to do here is just use filter map combined with string.toInt. And that's going to say, all right, so for each one of these items, try to turn it to an integer. And if it fails, just discard the result. That's what the filter part is. So now we have a list of these numbers. So we have a list of numbers. So just to quickly show you kind of what how we're transforming the values over time. We start with a string. String.lines gives us a list of strings. These are just comments on the right side. And when we do list.map, string.split, we're going through each item in our list, and then we're splitting each string up into its own list. And then finally, we do this, and that's what we're seeing on this side here. We have a list of lists of integers. So that's kind of the current state of things. I'm just going to save that real quick, but what we need to do is we need to turn this into a data structure where we can start asking questions like, is this tree on the edge? Basically looping through all of these. And I think the best way to do this is to is for each item in the list, I kind of want to like associate it with its coordinate. So I think what I want to do is do a list.indexedMap. And what I'm going to do is I'm going to say to S2 tree with coordinates. So to trees with coordinates is going to be the first function that we define here. So index map is a function that's going to take in the int, which is going to be like the index in our row. So when it goes through the first one, this is going to be index 0, this will be index 1, index 2, index 3, and index 4. And so that's going to represent kind of like our y height through the thing. So each item is going to be a list of integers. And what I want to return is I want to return a list of like coordinates and heights, so like tree heights. So if you give me a list of these numbers and the int, my goal is to give you a coordinate and tree heights. So a coordinate's a type I just made up. So a coordinate is just an int and an int, so like x comma y. And then the tree height is just that number 0 through 9, which represents how tall a tree is. So in Elm, we can make these little type aliases to help make our code a little bit more readable. So really what these are, this is really just a list of tree heights. And then this is like the y index. So this is the y index. And the reason I say y is because each line is going to represent kind of like the height here. So you'll see that this is like index 0, index 1, all that kind of stuff. So I'm going to do that. And then finally, we're going to have our tree heights. And what we need to do is we need to do another list index map so that we can get the indexes of the columns. We can get the x indexes. So I'm going to say to tree with coordinate. And I'm going to give it all the tree heights. So this time that we're working with a list of tree heights, what we're going to have is we're going to have this function, to tree with coordinates. It's going to take in the x index, and it's going to take in an individual tree height. What I think we want to do here is we want to return coordinate tree heights. to tree with coordinates. So this is the x index, and this is the individual tree height. So if I return x index comma y index as the value for our coordinate, then I can also return the tree height as the second part. And so if we want, we can use a pair here. If we want, we could also use a record. So this we could say tree, and like tree could have a coordinate and a height. That's one way to do it. So we could say tree, but I'm not going to do that just because I want to turn this into a dictionary in a second, and we'll understand why that's useful. It's because we're going to want to be able to query for stuff by their coordinates. So I think this is good. Let me hit compile. Oh, tree. Sorry, that's not a type anymore. Okay, so now what we have is this nested list of lists. So we're left with a list of lists, coordinates, and tree heights. I'm going to kind of move this over here so we can see it a little bit better. But if you see how this is kind of formatting, you'll see that as we go from top to bottom, the coordinates are increasing by 1 in the y index. And then as we move from left to right, you're going to see that the x indexes are increasing. And then what we have here is all our values that we split. So this is helping us kind of organize the data so that we can work with it. And then I have a nested list of lists. We don't need these to be nested anymore. So we're going to use list.concat, and all that's going to do is it's going to flatten our list. So now we'll just have one list with a coordinate of the pair, which is the coordinate and then the tree height. And then finally, I was saying this earlier, I want to turn this to a dictionary. So a dictionary is a data structure that lets us look something up by a key. So if the key is the coordinate and the tree height is the value, and I import dictionary here, I'm going to expose the type too. What this is going to do is it's going to allow us to use the dictionary functions. So here, the dictionary lets us look up values. So you can say dict.get, and you can look up like values in the list really well. So this is going to be helpful as we loop through the trees and try to figure out like what the bounds are. Okay, so this is our group of trees. What we need to do is we need to figure out which trees are visible. So what I want to do is I want to basically get a list of these trees with visible coordinates, I think. So this is our dictionary. So find visible trees. And this is going to give me a list. Coordinates, I guess. That's what we'll try to do. We'll try to make this function together. So this is the part that's going to do all the logic. Now that we have a data structure that we can work with, instead of just like a raw string where it's going to be hard to ask the string for information, we've got a dictionary where we can like ask, hey, what's the height at 0, 0? And then the data structure can say, oh, the height's 3. So find visible trees. If you give me a dictionary of coordinates to tree heights, I will give you a list of coordinates where each coordinate is a visible tree. So this is our dictionary. So what we're going to do is we are going to get all the values or all the keys. It's going to be a list of coordinates. This is going to be every single tree coordinate in our map. And we can use dict.keys to do that. And what we're going to do is we are going to filter down the coordinates where the tree is visible. Is visible. So is visible is going to take in a single coordinate and tell us true or false, yes or no, is that tree visible? So what we can do is we can take this coordinate, we can also break apart the x component and the y component. xy as coordinate. And then let's say that we return true for everything. What this would do is this would return all the coordinates back in our list. And then when we wanted to find how many visible trees there were, we'd get 25 back. So if everything said it was visible, then we would get 25 trees, right? Because we have a 5 by 5 in this example. So all we need to do to make this puzzle work is we need to change the isVisible function, and we need to use that dictionary to be able to ask the question like what, are there, is there any visibility to the left, to the top, to the right, to the bottom? Okay, so I'm gonna say the next thing we need to do is we need to get the trees. So I'm gonna say get the height of the tree. Height of tree. So this is gonna be a tree height. Let's call this height. And this is gonna try to get the tree at that coordinate. So if I did dict.get this coordinate here, maybe that would give me a tree height. Maybe it doesn't find a match. So by default, we're going to say that the tree height is 0. So anytime we can't find a match, we're just going to say that there's no tree there and the height is 0. So this is the height of our tree. Then we need to know the tree coordinates, trees to the right. So this is going to be a list of tree heights. So trees to the right, what we have to do is we have to basically start at our coordinate, and if our coordinate was 0, 0, what we need to do to go to the right is we need to keep incrementing this x value. So x plus 1, x plus 2, x plus 3, x plus 4, until we're out of the bounds of the tree. So what might be useful is to have the minimum, I guess like the minimum x, the minimum or the maximum x. So this would be, for our example, the minimum x would be 0 and the maximum x would be 5. So we shouldn't see anything more than that. It's not true for every puzzle. But what we want to do, I think, is we want to take the coordinates. We want to, for each coordinate, we just want to grab the first value of the pair. So we just want to, if it's 0, 0, we just want to grab the first 0. If it's 4, 3, we just want to grab the 4. And then once we have a list of all the x values, so this is like all the x values, this is going to be a list of ints. What we want to do is just say, what is the list.minimum for all the x values, what's the smallest one we find? And same for max x. What's the maximum value that we get? So for this here, if I printed this out, min x, max x, I'm just going to print this out to the console so we can see what the output is. Hopefully what we'll see for min x is we're going to get 0, and max x we're going to get 4, because that's the maximum index. And then I'm just going to say false, and I'm going to comment this. We're going to leave that alone for now. Let me see if this is compiling. Okay, so here we get just 0 and just 4. We need to make sure that we use it maybe with default. If we get no x values, we're just going to default that to 0 also. So if we can't find a maximum, meaning like if the list is empty, we're going to say that the max coordinates are 0. But here you see that we end up actually finding them, so we don't need to worry about it. We can do this exact same strategy to find the y values. And just instead of grabbing the first item in our coordinates, we're going to grab the second. And then the y values. And then this is the same thing. It's just going to be the min and the max y. Cool. So in order to find the trees to the right, what we need to do is we need to do a list.range. So list.range, if you give it 1 and 5, it's going to give us a list of 1, 2, 3, 4, 5. So what we're going to do is we're going to start with a coordinate of this tree. So we're going to give it the x value of this tree, and we're going to make it go all the way to the max x value. So in this case, if we're starting at 0, 0, it'll be 0 for our x value, 1, 2, 3, 4, and then 4 we'll stop at, because as you can see, the value for our max x is going to be 4. So those are all our coordinates. And then what we need to do with each coordinate is we need to do a list at filter map. And then we're just going to try to get the value at that coordinate. So this is going to be the x. This will be the x index for our tree. We'll say, go to that x index and use the current y index for the tree that we're looking at. And give us back a list of tree heights. Hopefully what we get here, if we print this out, we're going to get a lot of output here. But this is going to run once for every single thing. So you'll see that when we run it for the first item, we're going to get x to max x. That's right. So x max x. I think this is right. Oh yeah, the heights are 0 for the trees to the right. Interesting. Anyway, we'll see what the values are here. We're just gonna keep doing this to get all the heights, and I think this will work. So we'll do trees to the left. So trees to the left are going to be everywhere from the minimum x to rx. And then we're going to try to get the heights. Oh, you know what? We don't want to include ourselves. So I think what we want to do is basically, since list.range is inclusive, we want to subtract 1 from basically saying starting at the left of me and going all the way to the end. What are these values? So this will be the same, but then what's going to be different is if we copy this, we're going to have trees above. And above is going to be starting at our x coordinate minus 1, going all the way down to the minimum y value. And then here we're going to have our y index. And then we're going to use our current x. So it's going to be, I'm just going to copy this because I think it's more similar. If we're going to go to the trees below, what we're going to see here is starting at the tree beneath us, going all the way up to the maximum y index. We're going to try to find the tree here with that y index. And then this will give us a bunch of lists of tree heights. And what we need to do is we need to, instead of returning false every time, what we're going to try to do is we're going to try to say, all right, so for all these tree heights, so if I say this, and the trees to the left, and the trees above, this is going to kind of put them all together in one list. This is going to be like all the trees. All trees in row and column. This is just going to be one big list of tree heights. Actually, I don't want to combine them. What I want to do is I want to say if any of these items, so like if I give it a list of trees, trees above, trees below, trees to the left, and trees to the right, the order doesn't matter. If any of the lists that we get have all trees shorter than ours. So what we want to do is we want to say, all right, so for each item that comes in the list, which is going to be a list of each tree heights, we want to return true or false. And so if this is all the other trees, we want to know that all these trees are shorter, I guess are less than or equal to our tree height. So our tree height is this. So I can call this our tree height. Boop, boop. And then we're just going to give this other trees. So list.any returns true if any of these conditions are true. So for any of these things, any of those return true, we're good. List.all is going to say every single one of these needs to be true, because that's what determines if something's visible. So I'm just going to define our less than or equal to, and then just, I'll give it two integers and a Boolean. We could also say two tree heights. These are just aliases for each other. So this is a long word. So this is going to be the value, and then this is going to be the, I guess the limit is the first thing. So if this value is less than or equal to our limit, then we should be good. This is the value we're comparing one at a time. So we're getting 23 less than or equal to, oh, sorry, I think it's just less than, right? Because if the tree is the same height, then we don't see it. 21 above, trees below. I'm going to test this with just one coordinate. So if I give it the coordinate 0, 0, I expect it to return 1. So this is saying that let's just kind of do some debugging, because I don't know if this is working the way that I expected it to. So the trees to the right, so this is the coordinates. These are the heights. So if we look at this, value here, the value 3, what we're seeing is, we're just going to print out our tree height. So Elm has these really nice debug log things that you can just kind of put anywhere you want and just print out the values of things. So we're seeing that our tree height is 3, and the trees to the right have coordinates, x coordinates, I guess. 1, 2, and 3, and 4. When we combine that, we get 1, what's our coordinate? So yeah, it should be 1, 0, 2, 0, etc. So when we're done with that, we get 0, 3, 7, 3, which is showing us all the trees to the right. So 0, 3, 7, 3. When we check to see if all the trees are shorter than ours, let's just imagine that we see if we debug.log, all trees are shorter than ours. It's going to give us true because other trees less than or equal to our tree height. So that I didn't expect. I expected that to be false, because I expected oh, you know what? It's because of these empty items in the list. Let me just delete this real quick. Okay, that is false. So what it's showing us is that trees to the right, when we pass it into here, this is returning false. Because it's finding a tree that's not less than or equal to that. So we're getting 7. Maybe we did have it right. Let me just add these back in and see what the actual answer to the puzzle was. Maybe I misremembered what the answer was. So it's saying that, oops. It's saying that 21 trees are visible. Oh yeah, 21 is the answer. What am I debugging this for? This thing just works. Okay. So I think our code's good. I just wanted to make sure that I was getting the right values for each of those. So maybe that was helpful to see that. But what we're doing here, I could probably get all these comments. Format is this button I'm hitting here, and that kind of moves some of the comments to a place that makes it harder to read. So we're capturing all the trees in every direction, and we're kind of using math to figure out what they are. And then, yeah, once we have this, we're getting 21 as our answer, and that's what the Advent code answer is supposed to be. So I'm going to save this here. I'm going to copy the link so that I include it in the video description below. Day 8. Got a little notepad off to the side here that I'm typing in. And so what we're going to do now is I'm going to use my puzzle input. When you sign in to Advent code, you're going to get a different puzzle input than I do. But what we're going to do is we're going to plug that into our little program. Let's see with this crazy big set if we get an answer. So 1679 is the answer. Cool. Yeah, so let's see if it works. Okay, so that's right. So that's 1 gold star. So for part 2, all we're gonna do is we are going to we're gonna get like a slightly different like answer, and we're gonna try to figure out what we need to change about our existing code with like a slightly different problem. Sorry, not slightly different answer. It's a little bit late when I'm recording these videos, so sometimes I don't say the words that I mean. But yeah, so let's continue to part 2 and see what kind of twist that they have. All right. Content with the amount of tree cover available, the elves just need to know the best spot to build their treehouse. They would like to be able to see a lot of trees. To measure the viewing distance from a given tree, look up, down, left, and right from that tree. Stop if you reach an edge or at the first tree that is the same height or taller than the tree under consideration. If a tree is right on the edge, at least one of its viewing distances will be 0. The elves don't care about the distant trees taller than those found by the rule above. The proposed tree has large eaves to keep it dry, so they wouldn't be able to see higher than the treehouse anyway. In the example above, consider the middle 5 in the second row. So the middle 5 in the second row. So looking up, the view is not blocked. The middle 5 in the second row. I thought some of the middle 5 items. I'm like, that's the whole thing. All right, so if you look up, the view's not blocked. It can see one tree with a height of 3. If you look left, its view is blocked immediately, so it can only see one tree right next to it. If you look right, the view is not blocked, and it can see 2 trees. It can see the 1 and the 2 to the right. And then if you look down, the height is blocked eventually. It can see 2 trees, one of a height 3 and one of a height 5. The tree's scenic score is found by multiplying together its viewing distance in each of the 4 directions. For this tree, this is 4, found by multiplying 1 times 1 times 2. However, you can do even better. Consider the tree of height 5 in the middle of the 4th row. So if you look up, it gets 2. If you look left, it gets 2. If you look right, it gets 2. And then if you look down, it's only going to see the 1. The tree's scenic score is 8. This is the ideal spot for the treehouse. Consider each tree on your map. What is the highest scenic score possible for any tree? Okay, so what we're going to do is we are going to go back to where we were before we ran this calculation. So over here, instead of finding the visible trees, what we're going to do is we are going to take this full list. Oops, is this the crazy big input? Yeah, let's back that up a little bit. So let's start with the sample input, and let's work with that. So we're not gonna find the visible trees. So we have our dictionary. So what we need to do is we need to have something like find visible trees, but it's going to give us a different answer at the end. So this is going to give us, so let's kind of, let's just modify this function. So instead of giving us a list of coordinates, what this thing's going to do is it is going to take in our dictionary and find the most scenic tree. So the most scenic tree is going to be a coordinate. I think we're going to use a maybe coordinate, but I don't know. I don't know yet. So a lot of this stuff is going to stay the same. Let me just return. I think we're just going to sort by most scenic. To scenic score. What is the scenic? Does it want the scenic score at the end? What is the highest scenic score possible? Cool. So all we're going to do is we are going to take, we're going to calculate the scenic score for each tree, and then we are going to get the max. So this isn't going to be a coordinate. This is going to be an integer, which represents the score that we calculate. So if we want, we could say type alias score and just say that's also an integer. So what we need to do is we need to make this to scenic score function. So to scenic score is going to take in a coordinate, and it's going to return a scenic score, or it's going to return a score. So for this coordinate, before what we were doing is we were going through each of these, and we were filtering out the coordinates there. Let's kind of take this kind of like back up a little bit, and what we're going to do is we are going to get the like the values for each thing. So left is going to give us a score, or I guess left is going to give us the number of visible trees, right is going to give us the number of visible trees, above is a number of visible trees, and below is a number of visible trees. So rather than us returning this Boolean with list.any, what we're going to do is we are going to just say above count visible trees. We're going to do the same exact thing. Oops, sorry about that. We're going to do the same exact thing, but we're going to do it for below. We're going to do it for left. We're going to do it for right. And then what we're going to do here is we're going to make a count visible trees function. And then this is going to be the value for below. This will be the value for left. This will be the value for right. So what we're going to do here is we're going to get our scores. And that is going to equal visible tree scores. So we got rid of the name is visible because it's not a true or false anymore. We're going to give it a coordinate. This will give us this, this individual score count that we saw before. So this is what we can expect here. And I'm just going to indent this. I'm going to compile this. Oops. Let me format this. So we get all our scores, and then just like the puzzle said, we're going to do scores.left times scores.right times scores.above times scores.below. And it's just going to keep track of all the scores, and then it's going to find the maximum. So all we have to do here is implement this count visible trees function. So rather than has all the trees shorter than ours, what we're going to do is we are going to see count visible trees. We're going to say we found 0 so far. 0 so far, 0 so far. That's how many trees that we've counted when we start counting. So this is going to have the count. This is going to have a list of tree heights. And it's going to return a count. So count trees. And we're just going to make a quick recursive function. So I'm going to get rid of I guess I'll leave this here for now. We're probably going to use this middle bit in a second. But we're going to say, in the case where our trees, there's no more trees left, we're just going to return the whatever count we have. But if we do have a tree height, and we have, oops, sorry, I'm going to call this other trees. First tree in list, and then we have the rest of the trees. What we're going to do is we are going to say if the first tree is greater than or equal to our tree height. So I guess these are all heights, huh? I should probably use better variable names if I'm gonna be trying to talk out loud and say this stuff. So this is the rest of the tree heights. These are gonna be the other tree heights. Okay, so if there's no items left in the list, we're just gonna return the count. So if we're at the edge of the map and we look to the left and we see nothing, we're gonna say, all right, return the count. In this case, it would be 0. But if we're looking to the left and we notice that the tree to the left of us has a tree height that is greater than or equal to our tree height, we are going to return count +1, and that's going to be it. So as soon as we hit a tree that is bigger than us, we're going to say whatever our count is +1, that's it. Otherwise, we did not hit a tree that's too tall, so all we're going to do is we're going to say keep counting the visible trees, but increment it by 1 because we at least saw this tree, and then we're just going to keep going with the rest of the tree heights. And so rest of the tree heights is going to get shorter and shorter each time we go. So eventually we're going to either hit this case or we're going to hit this case, and that's how we're going to have our thing terminate. Cool. So I have this. Find the most scenic tree. I think that's it. So just 12 is what it's saying the score is. The tree scenic score is 8. Let me make sure that I did this right. So trees left, below, right. Score left, below, right. Trees above, the trees to the thing. 0. I think the issue is, well, does this only count the ones in the middle? If I've reached an edge or at the first tree that is the same height. If a tree is on the right on an edge, at least one of its viewing distances will be 0. Okay, so I'm pretty sure that's right. We might be doing the math wrong here. Our count will add 1 to it. We can also do this a slightly different way. So this is 0. This is 1, and then this will be the, I think this is the exact same equation though, so I think we'll get the same answer. But what we do is we can return 1 plus. I think this also gets us 12, yeah. So that should work the same. I'm gonna do it the way I had it because we won't hit like a Stack Overflow. Okay, to scenic score, and then what's the maximum scenic score that we get? Okay, what I want to know is, I want to print out the scenic score for a certain coordinate. So all I'm going to do that is I'm going to use an if statement. So I'm going to say if coordinate is, so what were the examples they had in the puzzle? They said that if we look the tree of height 5 in the middle of the 4th row. So if we look at index 2, 3, it's saying we should get a score of 8. Bug.log, and I'm just going to print out that. Oops. I just want to print out what the scores are for this. Otherwise, I'm not going to do anything. We're just going to return the scores. So 2, 1, 2, and 2. Wait. Which one is the, which one is 12? Maybe this puzzle didn't tell us what the tallest tree was. And again, I'm just like psyching myself out. So what I'm going to do is I'm going to say if this equals 12, let's print out the coordinate. Let's see which coordinate it's saying has that score of 12. Oops. And then I'm just going to say coordinate. This is just a little debugging trick. So when I get 12, what coordinate am I looking at? So it says that 1, 2 has a scenic view of 12. So here I get 1, I get 2. How is that 12? Oh, sorry, it was 1 what? It was 1, 2? So at x1, y2. So at x1, y2, it's saying that I get 1, 2, 3. Sorry. 1 times 1 times 3 times 2. Okay, this is perfect. So now what we're going to do is we're going to print out what the scores are for this coordinate so we can get an understanding of what we're doing wrong. So if the coordinate is 1 and 2, then what I want to do is I want to print out a bunch of stuff. Cool. So I want to print out scores. We'll start with the scores. So it is saying that there are 3 to the right. Is it including itself? Have this correct. I don't think we need this anymore. I don't think that's being used. So it's saying it can see 2 below and 1 to the left. Okay. So let's see which one's wrong. So if I'm looking at 1, 2, I want to know this, and I want to know the value, the height of the tree, just to make sure I'm looking at the right one. Tree height. Oh, that's right. I don't have that. Dict get coordinate dict. So it's saying that there's a tree of height 5 at coordinate 1, 2, 1, 2. And it's saying that above, it's finding 2 trees. That can't be right. Because this first tree height is greater than or equal to our tree height. So we should just be returning. One, two. Let's saying above it finds 2. That's wrong. So our logic's wrong. Let's see what the trees above are. Guess what I can do is... Oh, look. This is me being a elite hacker. So it's saying that for 1, 2, we're getting that. I want to see what the trees above are. I want to see what that list is. So we're gonna it's saying 0 and 5 are above it, which is right. Oh, it's going in the wrong order. Oh my goodness, that's what's happening. I'm not going outwards. So I need to be going in the opposite direction. So what's happening here is this range. When I'm going above, I need to reverse the direction of this thing. So I'm working 5, 0, not 0, 5. Oh, I feel so silly. Okay, that's all it is. So above and left need to be flipped. So I think if I do that, I get 8. Okay, that's what I was doing wrong. So yeah, so the issue is, yeah, I was just doing the trees backwards. I was starting from the top. I was saying, okay, 0, 5. Oh, I see 2 trees, but I needed to be going 5 and 0. So that was the issue there. Okay, well, let's see if this works for our puzzle input. So I'm gonna save this. Part 2. That was a lot more confusing than it needed to be, huh? Sorry about that. Okay, so we have that. All we're gonna do is try it with our puzzle input. And hopefully it works, because I am a sleepy boy. 536625 is our answer. Awesome. Okay, we got both of them right. That was a really annoying one to debug. But yeah, really leaned in a lot to debug log. Let me show you the debug function real quick. In case you run into something you don't understand in your own programs, there's a few functions of this module which are only available when you're in development. So when you actually compile to production mode, the Elm compiler will throw an error and say, hey, you forgot to remove a debug log. So if you've ever had a console log in production that said like fart or something goofy, Elm protects you against that. So all these functions are helpful for just trying to figure out why a program isn't working. One of them is just turning anything into a string. Debug toString is what we've been using in all of our problems, and that's just been to be able to see stuff in HTML on the right. Debug log is what I was using, where it works really great in pipelines because what you can do is you can kind of print like a label and then whatever value you're looking at. So debug log was helpful there when we were printing out like, what's the coordinate here, but still return the coordinate, but just let me know what it is. Let me kind of like attach like a little console log in the middle of this. And then debug to do is great for placeholders. So again, these won't make it into production. Your to-dos actually will break your build, which is great. So this is a technique I use at work all the time. When I want to come back to something, but I'm like in the middle of like a refactor, I'll just throw in a debug to do. And if I push that code, even if it gets approved, by like a code reviewer, our CI fails because the debug to do does not compile in production mode. So yeah, so that's it. We had a lot of fun. That was an easier problem, I think, but I just was really struggling with I think all the how verbose it was and trying to visualize that stuff in my head. So hopefully it wasn't too confusing for you. But all the source code is available. It's in the video below. And yeah, hope to see you on day 9. And take care. Goodbye.